Hello everybody, welcome back to another Gregorius Maths video. It's day 6, I believe, of the Advent calendar. And yeah, today we're pressing on. We're getting a bit of an algebraic number theoretic flavor to the Advent calendar now. And what we're going to be proving today is a very special case of the Catalan conjecture. So we're going to be showing that the only integer solutions of x cubed equals, I said x cubed and wrote the wrong thing, of x cubed equals y squared plus 1. The only solutions to this are integer solutions are y equals 0, x equals 1. And yes, this is a very special case of the Catalan conjecture because the Catalan conjecture says that no two consecutive perfect powers, there are no two consecutive perfect powers apart from 2 cubed and 3 squared. And this one is telling you that you can't have you can't have a perfect square immediately followed by a perfect cube. So yeah, this is what this is telling you, which is a neat result. And more importantly, the method that we're going to use to get to it is something that can be done, it showcases in general why algebraic number theory can be powerful at sort of an elementary level at least. What's our approach going to be? Well, we're going to factor this guy here as y plus I times y minus I. So immediately now we're not even looking at integers anymore. We need to expand ourselves to the Gaussian integers. So we're going to look at this equation in closer detail within the Gaussian integers, which are just the set of all complex numbers a plus bi, where a and b are both integers. And then once we've extracted some useful information about this equation from looking at it in this sort of more broad context, then with that information, we travel back home to the integers and we show the final statement, basically. It's the general approach. And the place where algebra comes into it is because I'm just going to be assuming, or I'm going to be going with the knowledge that I can say that I can basically work with primes in here in exactly the same way that I can work with primes in the integers. But of course, that for just like a general ring, you know, that may not necessarily be true. So you need to do a bit of algebra to show that what I'm doing is sound. But yeah, I'm going to just be working with primes as you would in the integers. And in this case, that is actually allowed because the Gaussian integers are sufficiently nice. So yeah, let's get cracking. First things first, as promised, we're going to factor this. So x cubed equals y plus I times y minus I. Okay, cool. Now, the next thing that's nice about y plus I and y minus I is that in the Gaussian integers, these things are coprime. And the way that we're going to show that is we're going to assume that they're not. So assume that there is some alpha that divides both y plus I and y minus I. And what we want to show is that this alpha must be a unit. So a unit just means plus minus 1 plus minus I, because if we don't allow for units, it's sort of like, imagine in the integers, right? If we want unique factorization in the integers, we need to allow for the fact that 2 times 3 is the same thing as minus 2 times minus 3. That type of idea. So yeah, in order to remain unique, in order to preserve unique factorization, we just sort of say that 2 factorizations are equivalent if you've just inserted units somewhere. So anyway, yeah. So we want to show that if alpha divides y plus I and alpha divides y minus I, then it must have been a unit. Cool. So if this is true, then that means that alpha must divide the difference. So alpha must divide y plus I minus y minus I, so just 2i. And notice that 2i is just 1 plus I all squared, because the 1 and the minus 1 cancel out. And, well, okay, it turns out 1 plus I is actually prime and in the Gaussian integers, and the reason for this is, if you take the norm of 1 plus I, and you assumed that 1 plus I was just some alpha times beta, then the norm of 1 plus I is just 1 squared plus 1 squared, which is 2. So you get that 2 is equal to the norm of alpha times the norm of beta. But 2 is prime, so that means that either the norm of alpha or the norm of beta were were 1. And so this means if you have a norm of alpha equals 1, then alpha must have been a unit. So this means that either, and again, I shouldn't have used alpha because I've already used it here, but that's too late. Either alpha or beta unit, which implies 1 plus I is prime. Okay, now, since 1 plus I is prime, what we can say is, if alpha divides 1 plus I squared, and alpha is not a unit, because if it were a unit, it would sort of automatically be dividing it. So if alpha is not a unit and alpha divides 1 plus I squared, well, think about it. If alpha divides p squared for some prime p, then we must have that p divided alpha. So, by unique factorization. So therefore, we have that 1 plus I divides alpha. And therefore, since alpha divides both this, and x cubed is equal to the y plus I times y minus I, this means that 1 plus I divides x cubed. But again, 1 plus I is prime. So if a prime p divides x cubed, then it must have divided x. So this means that 1 plus I divides x. And so therefore, we can say 1 plus I squared divides x squared. And therefore, 2i divides x squared. Here's where we run into an issue. Here's where we get our contradiction. If you look at this equation here, this thing right here is telling us that x squared is even, so it's telling us that x is even, basically. But if x were even, then x cubed mod 4 has to be 0. However, if you look at y squared mod 4, if y is even, is 0, and so this would be 1, so we couldn't have that being true. So, okay, y is odd, but if y is odd, then y squared is 1 mod 4. And on the right-hand side, we get 1 plus 1, which is 2 mod 4, so we get 0 equals 2. And so in either case, if x is even, our situation is breaking down either way. And so x must be odd, but this contradicts this. And so we can't have that this is true unless alpha were a unit, which would not allow us to go from here to here. So we must have had that alpha is a unit. So this means that y plus I and y minus I are coprime. Again, when I say prime and coprime, I mean within the Gaussian integers. I just don't want to write that out every time. Okay, good. So now we have y plus I and y minus I are coprime. This is excellent. And the reason why this is excellent is because, think about it. Let's say we have some prime pi which divides x. If pi divides x, then this means pi cubed divides x cubed, right? But if you have pi cubed divides x cubed, we have pi cubed divides y plus I times by y minus I. However, these things are coprime, so they share no factors apart from units. So if we're contributing a prime cubed into our factorization, it must have come wholly from one of them. Otherwise, they would share a prime factor. If we got pi squared from here and pi cubed and pi from there, then pi would be a common factor. So we must have pi cubed is either coming from y plus I or it's coming wholly from y minus I. So in other words, if every prime factor of x, so we write x as a prime factorization, then we get, in terms of Gaussian integers here, by the way, and then we get that x cubed must be a collection of primes cubed, or more, but at least cubed, and each of these cubes must have come from wholly from one of these factors. And so what I'm saying is that each of these factors is itself a product of primes cubed or more. And so, therefore, we can say y plus I is equal to some, well, it's equal to some unit times some number cubed, but each of the units are cube numbers, so we can subsume it in. So it's equal to z cubed, and y minus I is equal to w cubed. So this is really good now. Now we're in business. Now we can take our information and run back to the integers. So let's look at this equation for a second here. Let's write z equals a plus bi. This means that z cubed is equal to a cubed plus 3a squared bi minus 3ab squared minus b cubed I think, if I've done the multiplication right, which is equal to, so let's break this into imaginary and real components. So we get a cubed minus 3ab squared where are we? Yes, plus 3ab squared, 3a squared b minus b cubed I. And we can factor out a b here, so that we get 3a squared minus b squared b I. So what can we say? Well, we know that the real and imaginary parts must be equal. So let me just write this equal to y plus I. And so we get the real part is y, and the imaginary part is I. So in other words, we can say 3a squared minus b squared times b is equal to 1. But we're working with integers, so there's not a lot of options left for us. We either have b is 1 and this thing is 1, or b is minus 1 and this thing is minus 1. So let's just go through each possibility. If b is 1, then we get 3a squared minus 1 equals 1, so 3a squared equals 2, which is bad. So b can't be 1. And if b is minus 1, then what do we get? We get, this thing is minus 1, so we get 3a squared minus 1 equals minus 1. So we get 3a squared equals 0, so we get a equals 0. So the only solution that we can have is a equals 0, b equals minus 1. And then we just plug this in here, which implies that y is equal to a equals 0, 0, 0, y equals 0. And then we plug this into here and we get x equals 1, like so. And this is our only solution, because anything else would break this, and we've already said that this must be true by the work that we did in the Gaussian integers. And yeah, there we go. There's a special case of the Catalan conjecture proven. And there are other cases that you can prove very similarly within the Gaussian integers, which you may want to fiddle around with. And you can also pass, you don't have to pass the Gaussian integers. Say, for example, I had like y squared plus 2 on this side, then I might want to factor it as y plus square root minus 2 times y minus square root minus 2 instead. And in that case, I'd be working with a different ring. I'd be working with the integers adjoin some other radical, some other imaginary complex number. Yeah, purely imaginary number. So yeah, this is like an example of the sort of general technique that one can use, where you pass to a bigger ring, take results from there, get your information, get this thing basically, this key idea, and then we travel back to the integers and we can find our solution. So yeah, there's a example of why algebraic number theory can be cool. An elementary example, don't get me wrong. It's a bit above my pay grade to go further than this, but yeah, hopefully you enjoyed, and I'll see you tomorrow. Cheers.